So greetings, let's say we have this theorem. There's a lot of written out, but basically the point is we have a sequence xn as it goes to infinity, and it has a real value, convergent value x, capital X, and sequence lowercase y sub n going to infinity has a convergent real limit y. And if x is smaller than y, this is the theorem. This is the theorem that you want to prove. If x is lower than y, the limit value is lower strictly than the limit value of the right sequence, x and y, respectively, then there will exist some real number. This is natural number, was a mistake, so a capital case N natural number, such that for any natural number higher than this natural number, so some lowercase n in naturals higher than this natural number, every term xn is smaller than y. So there will be some natural number, because sequences take natural number inputs. There will be some natural number that this natural number and all natural numbers higher than it will yield that the term xn and y respectively are in this relation, xn smaller than y, if the limit value is strictly lower than y for x. So let's prove that. Well, here is our furthermore written out the limits definitions for the two sequences. That says that for each of them we chose some concretely named natural number beyond which the sequence term is very close to the limit value. The same goes for here. We chose n1 and n2 respectively as these natural numbers for the two sequences. But let's also, we'll use this in a second, but let's also call something a max. So let's say natural number n max will be the maximum of the two n1 and n2. So these two sequences have some natural number inputs beyond which they are very close to the limit value. And if we take the max, we take, to be safe, the max of the two values. And that, so let's set n max, some natural number, whatever of these two, n1 or n2 is higher. Choose that higher one. Max takes the higher of these two numbers. So we have this n max now. And let's now continue with the proof. The proof is basically based on, like many other epsilon proofs, we choose some particular value of epsilon. And there's some more choices. Probably the easiest choice would be y minus epsilon to set it equal to y minus x over 2. But let's set it to 3 just to show that that would work as well. So 3. It will be a little bit more complicated, but then you can also try for yourself too that it works as well in a very similar fashion, the similar idea. Well, so if we chose some natural number n max, that's the higher of the two n1 and n2, then we can start actually building a sort of chained long inequality expression where we will show that xn is strictly smaller than yn when all these things are fulfilled. I would start with actually realizing that these expressions for the limits, they say that after some n1, xn minus x is between minus epsilon and epsilon. That's what an absolute value says. So xn minus x is between epsilon and minus epsilon for its n1 condition, and according to the yn is the same story. Yn minus capital Y as its limit value, but higher than minus epsilon, lower than epsilon. We set epsilon equal to this. And now we can sort of start with an expression that's a chain inequality to conclude or get to the main point of the proof. So xn minus x should be smaller than epsilon. And now we're going to build towards the right until we say it's more strictly than y. That's the goal. But xn minus x smaller than epsilon, because we set epsilon equal to a concrete value like this in terms of y and x, I could add x to both sides. So I can add x to both sides and I'll have epsilon plus x. But if we take the value of epsilon right here, common denominator, and we'll actually get y plus 2x over 3 for that. But we still didn't get to yn. We need this to be smaller than y. We want to show that. Well, actually, this set value of y that we chose, sort of arbitrarily, but in a way, it's the biggest trick for the whole thing to work. Probably the most tricky part of the whole proof. This thing, we can rewrite the equation to get some more information or to see the information from more sides. So 3 epsilon is equal to y minus x. And because we got to epsilon plus x, we saw that it's equal to this. But let's see it equal to just directly y and epsilon. So we can finally add some lowercase yn that we want to the whole inequality to sum up the proof. Well, if this was true and this is equal to this, let's give it one more equal sign and make it equal to yet another thing, and that will be y plus epsilon plus x. What is it equal to? Well, epsilon plus x, according to this equation, is equal to y minus 2 epsilon. Algebraic manipulation here. So y minus 2 epsilon. And now it doesn't look very symmetric because we chose the 3. If we chose 2, that would be nicer. But anyway, in any case, we have y minus 2 epsilon. Epsilon is something that's making y strictly lower than yn after its set natural number input, and we took even the max of the 2. So by the way, this thing applies for n max. So take n max, and then this thing we work with this. All right, that's why we took the n max, to make sure we take the higher of the 2. Whatever they are, we can just pick the higher of the 2. Okay, and y minus 2 epsilon should be, if you remove epsilon from y, you're already below y, and 2 epsilon is also fine. So y minus 2 epsilon is strictly smaller than yn. Beyond some natural number, n1, n2, well, we took the max, so we're safe for that. And so y minus 2 epsilon is strictly smaller than yn. And this is the main point here, because now we got xn strictly smaller than yn. And that's the proof's main point here. We go there, okay? So we basically set epsilon equal to something concrete, and we prove that if x is strictly smaller than y, then there will be some natural number n beyond which xn is strictly smaller than y, and we have that, all right? And we found that we can look at that natural number input beyond which that applies as we choose the n1, n2's max, and then we wrote out this inequality chain expression, and we got there. We got xn strictly smaller than y.